Hello everyone and welcome to this video on propositional logic. Let's get right into it and begin with the notation and terminology we're going to be using. So what is a proposition and what is propositional logic? Propositions care all about what is true and false. We can say, for example, that it is raining. So we have some variable p and we've assigned it to the statement it is raining. P then is either true or false. It either is currently raining or it is not currently raining. We have those two binary options. The binary because while P can be true or false, it can also be 0 or 1. Both are valid representations of truthness and falseness. So that is a very simple thing. We have P and what's called an atomic assertion or atomic proposition, which is one singular thing in an atom, so indivisible. It is raining. Let's say we also had some other atomic proposition, which was it is Monday. So we have P, and then we can have R. We'll say this is it is Monday, which again is either going to be true or false. Then there are various things we can say. For example, if it is currently raining and Monday, then we can say it is raining and it is Monday. So we can say P and R. So we'd expect this entire statement, which is still a propositional statement, we are just combining these things together into a compound, is that entire thing to also equate to either true or false. We have created a propositional formula or a compound formula. So propositional logic at its base is all about making these propositional atoms and how we can combine them together using various different operations to model the world. And there are other types of reasoning other than propositional, but that's what we're discussing. It has its limitations, but it's very, very good at certain tasks and can be built to produce computers. Computers are built on propositional logic theory. So I here mention and. What does and mean? Well, if you have P is true and R is true, then this entire statement, P and R, is true. If either of them or both of them are false, well then logically that doesn't follow anymore, does it? You can't say P is true and R is false and have the entire statement, be true. Doesn't make sense. And is by definition saying that both of these things hold, so both of them must therefore hold. What other operations can we discuss? The simplest, perhaps, is not. Not is simply what we have. It's called not, or it's called negation. These operations often have multiple names. Going forward, I'm going to have a generic propositional formula called P to reference these things. P and I think Q is the other common one. P, Q, R, that whole bit of the alphabet. S and T are often used as well. That section is where we're usually working with when talking about propositional formulas. So, to show what not does, we're going to want to use what's called a truth table. So what we do is this is a column. In the column for P, we go over its possible values. In this case, it can either be false or true, 0 or 1. And then in the next column over, we show what its what the not of P or the negation of P is, and we use this symbol here to show that. This sort of right angle. And what this does is it simply flips the bit. This is binary. It turns a 0 to a 1 and a 1 into a 0. Very simple. It's not a negation, but that is a not. And there are other symbols you can use for this. This is one of them. Sometimes you'll have P hat. But most common and the one I prefer most is this this symbol here, which on a keyboard is usually to the left of a 1 on a British keyboard. So that is not. Let's move forward now to, as I mentioned before, and. So now we have and. This is also called conjunction. Again, these have multiple names. Important to be able to recognize it according to either of them. In set theory, this operation is also called union, for example. And there is a lot of similarities between propositional logic and set theory. They are underpinned a lot by the same things. So here we have P, we have Q. So two propositional formulas, because while not is a unary operation on one operand and works on two operands P and Q. It is a binary operation. So we have 0, 0, 0, 1, 1, 0, 1, 1. A tip for making these truth tables, count up in binary. This is the binary for 0, this is the binary for 1, this is the binary for 2, this is the binary for 3. So you're trying to figure out how to make, you've got them all. First of all, you should have the number of bits long it is. In this case, it's too long. It should be 2 to the n number of columns. Number of rows. We have 4 rows here. 2 to the 2 is 2. 2 to the 2 is 4. Correct number of columns. And when you're saying which goes where, just add up every single time. Add 1 in binary, and you'll go further. If you don't know how to add up in binary, that's the next video. Now moving forward, we have P and Q. Is a symbol. We have this similar to the power of operator sometimes used. It is a vertical chevron, I think that symbol's called. I'm not sure. And simply states that it is 0 unless both are true. So if you give it a P and Q, then you get both of 1, you get 1. Otherwise, you get 0. Moving forward, we have or disjunction. This also is a binary operation, so it has two things, and we show it using some P or the opposite of the and upside down Q, so like a V shape. And again, if we have our truth table, then the operation P or Q is going to be true if any of the two inputs are 1. So in this case, this is the truth table for or disjunction. Moving forward again, we get to equivalence. Now we are moving away from the typical and most common operations. Equivalence is a bit more niche, but still generally well known. It simply says, are the two inputs the same? So we have again our P and our Q. So we have P, and it's a double-ended arrow. Oftentimes it is also too thick. So it's like an equal sign of arrows on the other end, like so. And equivalence is true if P and Q are equivalent to each other. So 0 equals 0, 1 equals 1, but 0 does not, equal 1. So we have 1, 0, 0, 1. This is a truth table for equivalence. Finally, we have implication. So this is if we have P and Q, and it has P, similar to equivalence in the operation, but it's only a one-way arrow to Q. In this instance, the truth table, don't try to understand it, it doesn't really make any sense, is this one. It makes sense over, it's sort of in this section. If P is true, because that's how you can read implication. You can read it kind of, if P, then Q. That's the idea behind it. If P, then Q. So if P is true, then Q must also be true. But then you have the fact that, oh, pardon me. I copied the truth table over wrong. The one right is upside down. There. And that kind of also makes it for true falses. If false, then false. So sort of, your top one and your bottom one kind of makes sense, logically speaking. If false, then false. If true, then true. But then you have, and this also makes sense. If true, then false. Well, that should be false, shouldn't it? That doesn't make sense. If true, then false. Not quite make. But then you have if false, then true, because for some reason this one is this one's true. The reason why is because the truth table was made because there was no name for this truth table, and they called it implication. If I understand the history correctly, the truth table was made first, then they named it, not the other way around. They needed a name for this truth table, and they happened to call it implication. But yeah, remember truth table. It's a fairly simple, truth table to remember. Really, all you need is this row, because it's the only unique one. If you give 1 of P and 0 on Q, then you have 0. Otherwise, you have 1. But that is all of our basic truth tables. There are others, exclusive OR, for example. which states, oh, it is OR, but we get rid of the bottom row. We say that if they're the same, then it is 0. In essence, it is the opposite of equivalence. If you were to say not equivalence, then you would get 0, 1, 1, 0. That is XOR. We don't include XOR as the fundamentals, and as it is actually, you can create all of these using a combination of ands and nots. But these are the ones we care about, typically, in the fundamentals of propositional logic. The others can be built up further, or have more niche uses. Now, let's discuss some theory behind how we can show these truth tables in a more mathematical sense. We are going to discuss interpretations and also valuations. So first, a valuation, well, both of these correspond to a truth table. So I'm going to quickly write up the truth table for, let's say, OR, so P or Q. Now then, a valuation is a function which corresponds to these two, specifically. So a valuation corresponds to our inputs. So every row in our truth table for our two atomics, in this case 2, we have some function which, given those, will give out the values they have. So for example, say we have 4 valuation functions, v1, v2, v3, and v4, one for each row. Then v1 of p is 0, v2 and also v1 of q is 0, v3 of p is 1, and v3 of q is 0. So a valuation simply takes in a proposition and tells you what the output is, what it corresponds to. So it maps this proposition to each of these values. So, to reiterate, a valuation is a function that, when given a proposition, will return a binary true or false value. It evaluates a proposition to its binary equivalent. And each row in a truth table, especially for the atomic columns, have their own valuation function. So a 4-row truth table will have 4 valuation functions for it. That's what a valuation is. Now, what is an interpretation? Well, as evaluations do the atomics, interpretations deal with the thing we're actually trying to compute. They deal with the outputs. So an interpretation is a function which takes in both an valuation function, or its products, and a formula. So, for example, these things here could take in some interpretation I, and you would give this your P or Q, and you would also give it your, for example, V1. Another way of writing this, more commonly, is just to simply label it I1 to make it correspond to your valuation 1, and only pass it the formula. Both works, and in this case, it is 0, and for all others, your I2 is going to be 1, because that's what it does. So an interpretation is a function that evaluates some formula in respect to some valuation to give a binary result. So the thing here has 4 interpretations as well as 4 valuations. So this is the mathematical way of representing a truth table. And it is important to remember, to know, that if there exists for given some propositional formula P or whatever, if there exists some interpretation of that formula for which you have 1, then that formula P is said to be satisfiable. So each of these, so this, and this, Those three interpretations, so I2, I3, and I4, these all satisfy P or Q. Each individually satisfied because they have an equality of 1. They evaluate to 1. So if you evaluate to 1, then you are satisfying that equation. Those valuations satisfy P or Q. Any formula for which there is at least one interpretation which satisfies it is said to be satisfiable. Or in other words, if a formula can never have an interpretation which returns 1, it is unsatisfiable. For example, you may have P and not P, which is impossible to satisfy. All its interpretations are going to be 0 for your two values, 0 and 1. I guess you could also do not P here, which is 1, 0. So see here that you have an impossible to satisfy thing. There are no interpretations which satisfy it, so it is unsatisfiable. Now, that's everything to do with valuations and interpretations. But keep in mind because we are sometimes going to refer to those in future. Before we move on, though, to anything else, let's discuss a common problem, which is the combinatorial explosion, as a quick aside. So, regularly when you're trying to determine if some formula is satisfiable or unsatisfiable, or when you're working in things related to propositional logic, you can run into the combinatorial explosion. Also comes up in binary numbers a lot. This simply states that if you were to have some formula with n atoms, then the number of valuations or number of interpretations, therefore, is going to be 2 to the n. So if you have a sufficiently large n, you are going to have an incredibly large number of valuations and interpretations. In other words, you're going to not be able to check them all if n is really big. So this is a problem that often comes into if you're trying to determine is something satisfiable. If it has a lot of atoms, you might just not be able to check because there's too many. Similar to the chess problem. The number of unique states in chess is greater than the number of atoms in the observable universe. You cannot look at them all. There is a set of algorithms called SAT solvers, but we're not going to be discussing that. But they use heuristics to kind of figure out the ones which logically shouldn't be checked. So we reduce the search space down from such an absurdly high 2 to the power of n. But quick aside into the combinational explosion of noting that for very large n, we do have this issue. Let's move right on to a method of interpreting and reasoning about these propositions. So propositional logic is a type of logic, and logic is for reasoning. So with this, and what we're about to discuss now, this is how we can say, here's what we know about our model. So we have a bunch of propositions which describe something we're talking about. And here is something we want to know, or something we want to query about our model. So we have some other proposition. So in this case, we have what is said to be the set K of known propositions, and the set S, oh sorry, not the set S, misread, the proposition P. Let us have an example, a very simple example. Say we have K equals P and Q. So these formulas are simply atomic, very small. In this case, we are questioning, we're going to say this symbol here, which means follows from. We're querying a set of propositions formula, notation. And then we're going to say some P, which is going to be, we're going to say some S, P, and Q. Shouldn't have named these two P and Q. So we have some S, which is the thing we're querying, which is looking at this formula here. So we're asking, in other words, does P and Q follow from K. In other words, given what K tells us, can we also say P and Q? The important thing to remember is what we have in K is true. So P is true and K is true. That is what K tells us. It tells us these are given facts. P is a fact and Q is a fact. Therefore, is P and Q also a fact? Can we reason that? So let's show the process of doing so. In this case, we'll go through all of the atoms and all the propositions and formulas in our K. We'll write them out. We're going to say P and Q. This is going to be a truth table. And we'll write out all the combinations as usual. And we'll also write out the thing we're querying. So P and Q. And we'll write out how that works as well. Now what we do now is for every single formula within our K, we will remove any row where those are 0. Because again, K tells us these are true. So the first row will P is 0, we don't care about it. Also 0 in the second row. In the third row, Q is 0, we don't care about it. K tells us this isn't in our purview, which means we only care about this last row, where both are 1. Now, once we've done this, we've reduced it only to those rows, in this case there's only one of them, where all of our known facts are true. Then we will also look at our queried thing, which is on the right here, and check if that is also true. If for all rows it is true, it is, then we say that this does in fact follow from our set K. So this is how we can verify this information. And logically, this makes sense. You can see how the logic works here. Let's look at some more slightly in-depth examples. Show that P1 or P2 follows from our K of P1 and P2. So what we do here, we draw out our truth table. So we have atoms involved of P1 and P2. We're also going to have to write out everything within our set. So we have P1 and P2. And finally, we have the thing we're querying. So P1 or P2. And we'll go through and write out all of our values. There we go. And now we need to identify all rows where our given facts are false and eliminate them. So in this case, we don't care about P1, P2 because they're not given. We do, however, care about P1 and P2 because that's the only given. So going through this, we don't care about this row because it's 0, and it's 0. So these eliminate their rows. So what we have left now is this final row. And if we now look at our queried formula, it's 1, so this follows. Fairly simple process. Again, another example. Let's show that if we have some set which contains only P1, show that P2 follows from it, or does it. In this case, we're going to say show that it doesn't follow through. Also, we say that in this case, in our previous example, we said P1 or P2 holds under the dataset P1 and P2. So holds or follows from, depending on your perspective and which one you're saying in regards to the other, can both be used. So here we do the same process. We have our P1, we have P2, we do our values 0, 1, 0, oops, pardon me, it's supposed to be a 0, 1, 1, 0, 1, 1. We are told this one, so we can eliminate this row and this one because of this. Now we have these two, so now we look at what's remaining and we identify where this is true, because this has to be true on all of them, and it's not. So it does not hold under our set K. So in this case, it does not hold because we have that instance there. Now that is everything for this section. Let us move on to logic circuits. There we are. Logic circuits let us make a diagrammatic version of propositional formulas. They represent, among other things, how computers are created. Not created, but how they are structured. At the very, very basics, a computer is just a bunch of logic gates strung together. So logic gates correspond to all of those operations we had before. However, we only really care about 3 of them because they are the most common when actually talking about logic circuits. This is AND, OR, and NOT. It is a common habit to write logic gates in all capitals. So going through, say we have AND first, so we have 2 inputs, P and Q, and we have some output R, and we want a graphical way of representing this. We do so with a kind of D shape, so a flat left-hand side and a sort of curved on the right. We just draw these lines to show that they input. This is the exact same operation as logical AND, as we discussed it before. This is equal to R equals P and Q. Or, very similar, we have RP input, RQ input, R output, and we draw this similar to AND, but more pointy. So it's got a curved inward and a more slanted front. Something like the Star Trek symbol, vaguely. And this again, R equals P or Q. These are equivalent to each other. And NOT simply says that we have P and R, or P and not P, with our symbol being a triangle, with the important part here, the dot on the end. Actually, the dot's the bit that means negation. This comes up a lot. Simply, if you have an additional very common logic gate, NAND, this is an AND gate with a NOT gate at the end. We represent it with the blibble there as well. It has a name, I can't remember what it is, but that blibble is actually the bit that means negation. The triangle is just so we have a symbol. I think it's also because it's sometimes used diodes when using circuitry, and triangle is a diode. Not quite certain about that, but the circle is the bit that means negation. And yeah, this is equal to R equals not P. These are the 3 we really care about. There are others, as I said, XOR, NAND, NOR, everything else. But these 3 are sort of the basics, even if you can make make OR from ANDs and NOTs. And then one final point is that if you have 2 inputs for AND, you can also have 3 inputs for AND. So you could have P1, P2, and P3, which all lead into some R, like so. Like that. Because this is equivalent to simply saying P1, P2, P3 with an AND gate here, an AND gate here, and then these connecting like so with some output here. These are the same thing, so what we have left is the n-ary input, in this case n equals 3. This is the n-ary AND gate. This is where you can do this. It's often shorter and quicker to simply do this method while the more long-winded method on the right. Now we've introduced circuits, we can start to discuss what is called disjunctive normal form. Remember, disjunction is OR. So this is disjunctive normal form. This is a grammar, so a specific type of writing propositional equations, and also structuring logical circuits and propositional circuits. It has several rules for a proposition for a formula to be in disjunctive normal form, often abbreviated to simply DNF. First of all, you're only allowed AND, OR, and NOT. You may not use any other operations. Second of all, if you have a NOT, it can only be attached to a literal or an atomic value. So this means that you can have not P, this is fine, but you cannot have not P and Q. This is not fine. So it can only be attached directly to atoms, not to nested structures, such as this nested and here. The third rule is that you can have ands within ors, but not ors within ands. What this means is that you are allowed to have, for example, P and Q all wrapped up with or S and T, but you may not have P or Q and S or T, or some other variation. It must be in the form of ors and disjunctions are used to connect multiple conjunctions together, but not vice versa. So these nested bracketed sections must always be conjunctions, they cannot be disjunctions. Now finally, there is one last optional rule, which is that if in every single conjunction there is every variable appears, then you are in full DNF form, full disjunctive normal form. So if the previous three apply and the fourth applies, you're in full disjunctive normal form. However, if only the first three apply, you're in regular, normal, disjunctive normal form. So let's look at some examples, also as an aside, for anyone who is interested in grammars. Oops. This is the grammar for disjunctive normal form. Should you be interested, not really need to know this, but for those who like that such information, there you are. Now let's look at some examples. Say we have, there's my pen, A or B. This is in disjunctive normal form. It is not in full disjunctive normal form. Oops, missed my D. D, N, F. Because you do not have a conjunction on this A, and you don't have a conjunction on this B. Full disjunctive normal form must always take the form of a bunch of conjunctions for every single variable with a bunch of disjunctions connecting them. If you had another thing here of A and B, or A and not B, or not A and B. This is in full disjunctive normal form, and it's also equivalent to the first equation. So this and this are equivalent to each other. They have produced the exact same truth table. However, the second one is in full disjunctive normal form. Terrible for us to read, but for machines, much more nicer to work with. So that's why we have it. Now, if you want to construct a disjunctive normal form of some arbitrary equation, you want to look at its truth table, because it's a very simple way of creating these equations. So let's look at the example of P or Q and not Q and R. So you can see for various reasons, this is not allowed as disjunctive normal form. But how can we turn it into disjunctive normal form using a truth table? Well, first off, we want to draw the truth table. So we have a P, Q, R. We have going to be 8 total rows because 2 to the 3, and we draw them all out like so. Very neat. And then we can draw out our truth table. So it is P or Q and not Q and R, like so. So look at this, we have an and in the middle, so any instance where this fails is going to break. So let's look at P or Q, it's when they're both 0. So that means this is 0 and this is 0, because that's when they're both 0. And on the right, it's going to fail when Q and R are both 1, because it gets negated. So when Q and R are both 1 is here and here. Now, all of the points it should give a 1, I believe. But let's test it. So 0, 1, 0. So this passes as a 1. And on the right, we have this passes as a 0, so it gets negated, that gets turned into a 1. That's our first 4. And now for these ones, 1, 0, 0. This gets passed, this fails, this goes to a 1. Fails, and then fails. So 1, 1. We have 1, 2, 3, 4, 5, 6, 7, 8. Yep. That is our evaluation of this, of our various interpretations. Now, to turn this into a disjunctive normal form, we must take this and look at all rows where the interpretation is a 1. We don't care about the zeros. So we're going to identify this row, this row, this row, and this row. Now, all we have to do is create an evaluation of this. Oops. We need a propositional formula for each of those rows in their valuations. So we need a propositional formula to represent P0, 1, 0, 1, 0, 0, 1, 0, 1, and 1, 1, 0. So let's start off with 0, 1, 0. How can we get true out of that? Well, this is going to be not P and Q and not R. If you have this equation, then this will return 1 when we have 0, 1, 0. We do the process for the rest. We have P and not Q and not R, only using not and only putting the nots on atoms. Similarly, we have P and not Q and not R. Nope, just R. And finally, we have P and Q and not R. Now we have this. All we have to do is chain them together into a bunch of sections of a larger proposition. So we have this or this or this or this. And that is our disjunctive normal form for this. And I believe this will be full disjunctive normal form because it contains all the variables. This one happened to be full DNF, but usually I believe this would only give guarantee to give you regular DNF. This one just happened to work out. Now I've got that, let us move on to the next section, which is on combinatorial circuits. So a combinatorial circuit is a type of logic circuit which has two rules. First of all, when you are drawing the circuit, you may never combine signals from two different sources without a gate. So you cannot have some P and Q and combine them like this to then put them into, for example, a knot. This is not allowed. So what you'd have to do here for the same behavior would be P, Q, and then a simple OR gate going into the knot. Or NOR would work too. I don't think there's any limit here on using NOR and stuff, but usually you'd stick to just your regular AND or a NOT. So that's your first rule. Your second rule says that you may not recursively feed a gate. So you cannot feed a gate its own output. So it's invalid to have something like P leads into an AND gate, which goes into R and also goes into itself. This is invalid. This also applies even indirectly. So it says this is incorrect. You may not also have the same thing, which also midway along has a NOT gate, for example, which then splits and goes this. This is also not allowed. So there can never be a path from the output of one gate to its own input. Follow these two rules and you have a circuit which is combinatorial. So if we take a diagram of a circuit and want to turn that into a propositional formula, so for example we have P leads into NOT with an AND here, going over here into an OR, with input here going into a NOT, like so. In future, I will be skipping this drawing process, but for now, I think for the first time drawing a circuit, good to get manual to show the process. To interpret this, then, the best way is usually to go right to left, or in other words, outward. So we see here there is this OR on the end. This means that whatever our output R is, this is going to be dependent upon an OR. So the very middle of our equation, or the central pivot of our equation, is going to be an OR. On the, let's say, the right-hand side of that is very simply not Q. We can follow that line there. On the left-hand side, we have an AND. So we're going to have brackets here. One of which on the right-hand side is Q, and the left-hand side is not P. So this is the interpretation of that. This is the formula that corresponds to that equation, that circuit. We can say that two circuits are equivalent if they happen to have the same truth table. So if we were to have these two equations here, the left one is much more common than the right one, clearly, but they are actually the same equation. The left one just happens to be the right one in disjunctive normal form. I think specifically full disjunctive normal form. The right one is simply AND of P and Q or R. And this is the left one is the full disjunctive normal form of the right one. So they are entirely equivalent, but they are clearly very, very different. So in terms of efficiency of parts, the right one's better, but for processing power for computers, the left one can have its benefits. And as a side note, often denote this type of equality with a triple equal sign. If you've never seen that syntax before, simply means equivalent functionally as well. Now, finally, in this section, as well as combinatorial circuits, we have sequential circuits. These are exactly the same as combinatorial circuits, but they relax the second rule, which is about the self-feeding outputs. So you are allowed to do that. And by making that change, you can produce some more interesting circuits. For example, if you have some P going in, going into a NOT, like so, doing this, then you can feed it into itself and get rid of the input, and what you get is a clock. Because in terms of circuitry, when a NOT gate is initially powered, it has an output. So initially, if you're talking about purely deterministic terms, its input is originally 0, but in practicality it's random. Its input is initially 0, so it means it has a 1 on the output. So 1 goes back into feeding itself. That 1 then flips it, so it goes 0, and so the output is 0, which means it goes back into 0 on the input, so you constantly flip it between 0 and 1 and 0 and 1. And because there is a special delay in a logic circuit and how long it takes to process a change, and that is usually fairly consistent, you have a fairly consistent rudimentary clock. You've made as a clock. It will send 1 out at a regular impulse. Fairly rudimentary, but there's an example of what you can produce with this type of thing. Another more interesting scenario is what's called an SR latch. It's called a latch because it latches onto inputs. It remembers them. This is how we do memory. RAM is made up of latches. I'm not sure what latches actual RAM is made of nowadays. I imagine it's much more complicated and optimized. But the basic form is an SR latch. I'm not going to go into this because they're very, very, very interesting. And fairly complicated, but I don't want to give them justice there to go into them, and I don't have time to do that now. But they work by feeding input into itself. If you want to know more about them, look on YouTube. Tons of plenty of videos on YouTube. Ben Eater, for example, has some wonderful videos on them. And I believe there is also Sebastian Log, which who also has some nice animations about how these things work. So again, go on YouTube for those. Good videos there, but be aware they exist. So by a sequential circuit, you can use them. Fairly small part of the entire topic, though. Oops. Down my foot. There we are. Let us move forward to our laws. Now, depending on the order you've watched these videos, you may have already watched the set theory one, which is about, well, it has a section on exactly the same thing. In the fact, it's in more detail on the set theory side, because there's more laws that apply there, which I think often also apply here. So I'm going to go fairly quickly through these to save time, but we have the associative law, which says that if the brackets are on, if you have P or Q or R, and it also works for AND, as long as it's all the same, you can move the brackets any way you like, because it all is the same. You can correspond this mathematically to something like 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. The commutative law, which says that you can swap things around easily if you have, for example, 1 plus 2, which is the same as 2 plus 1. Order doesn't matter. If you have P or Q, it's the exact same as Q or P. The identity laws state that if you have P or the bottom, which is what this upside down T is, it means always false. Whereas the T is true or top. So we have top and bottom, which is true or false. If you have P or the intensification of false, then that is P, because P or 0 is wherever P is. If you have P or true, then you always have true, because the true always flips the or into the true case. If you have P and the bottom, then it can never be true, because one of them is 0 already. And if you have P and top, that's wherever P is, because P determines the outcome. In set theory, that equates to the null set and the universal set. Moving forward. The distributive law states that if you have some P and Q or R, then you can spread this out, you can distribute it by attaching the P using its AND on each of the Q and R independently. So we can see this here. We have P, Q, and R. So now we have P and Q and P and R, because this is the carbon here. This goes to here and here, and the OR gets moved to here. The same works if you flip all them, as is what the second line is. Now we have two left. The complement laws state that if you have P or not P, this is always true, because one of them has to be true. Similarly, if you have P and not P, that can never be true, because they're always going to be opposite. If you negate true, you get false. If you negate false, you get true. And if you complement something twice, if you negate it twice, you get the thing you started with. We have De Morgan's law, finally, which is that if we have some not P or Q, then we can split this up, flip the OR into AND negate each thing individually. So we see the negation moves here, and the OR turns into an AND. And the same works if you flip the OR of an AND of the OR, which is what the second row is. So those are our laws. Now let us move on to Boolean functions. So a function that takes, a function that maps some sequence of bits, so a single bit, is called an arity. For example, if we had a function that were some function f, which took in a sequence 0, 1, and mapped it to 1, this would be an arity. Why do we care? What's this got to do with what we're discussing? Because this is how we can represent a Boolean formula using a function. A circuit, for example, takes in some number of inputs. We have our P, Q, R. These come in. We might have an AND here, an OR here. This goes here, and then here, and then this. And then these might combine here into an AND go here. This takes this takes 3 bits and turns them into 1 bit. So we can represent this as a function, a Boolean function called an arity. there isn't much to say about these. Just as a final aside, these are Boolean functions. They're called arities, and they are an alternative way of representing logical propositions as well as circuits. And then one very final thing, which I'm just sort of shoehorning at the end here, because for some reason that's where it is in my notes, is the definition for NAND and NOR. So a NAND, as I did mention earlier, is a AND combined with a NOT. So if you have the truth table, it's going to be 0, 0, 0, 1, 1, 0, 1, 1, and it is 1 unless they are both 1. This is NAND. We can represent this as some P vertical line Q. Apparently that vertical line is called the Sheffer stroke. And it is equivalent to NOT, P, and Q. Similarly, we have NOR, which is for our three things, it is the opposite of OR. So it is only true when neither of them are true. We draw this P, vertical line downwards, Q, and it is equivalent to not P or Q. Again, just be aware of them. They don't come up too often, fairly rarely, I think. And NAND and NOR come up a fair bit, but the arrows in the vertical lines, less so. And again, to draw these, you simply draw the regular circuit and put a dot at the end. For NOR, it is our regular OR with the dot at the end. And that is it for this video. Originally this topic included binary numbers, but I'm separating them into a separate video, so thank you for watching. I hope this was useful.